Alright, this section is going to talk about the chemical properties of metals. So last video did physical properties. This is going to be chemical properties. I'm going to be hanging up in this corner on this video just so I don't have to keep moving around. But our chemical properties, these are going to describe how easily and how fast we react, or our elements react, to combined compounds or molecules. So how easily can something or an element kind of connect with another element to form something else. Sodium is going to react strongly with air and water, so it's stored in oils, so keep in mind with that, because there is water vapor in the air and sodium reacts with water, so therefore it will actually react with that water vapor in the air. It does that very easily. Gold and platinum are going to be high valued metals because they don't react easily with elements to form compounds. They kind of stay as themselves, and that's great because I like the physical properties of gold and platinum, being able to being malleable and ductile and conductive. Iron will be an example of something that's in the middle of this. It's slow to react with air, which is pretty much reacting with the oxygen because it's going to form iron oxide. Which is going to be that rust that forms on it is going to corrode. So a lot of times we galvanize iron, like we have galvanized nails, which means we're going to take that iron and we're going to cover it and coat it in zinc. And zinc is going to be less reactive to that. So in order for oxygen to get to the iron, it has to find a way through that zinc, which it normally doesn't do. So your nails will actually last longer in decking and stuff like that outside where it's constantly exposed to oxygen. Our first category is our first family. Remember, families are columns. They are up and down, first rows. Rows are across, columns are up and down. First family is going to be called our alkali metals. They are all going to react by losing one electron. That's all they need to do in order to combine with something else is lose one electron. It is very easy to lose one electron, so they are very easily going to react and combine with other things. And due to that fact, they are going to be found combined with other things in nature. For example, you don't find sodium outside. You normally find it combined with other elements such as chlorine makes sodium chloride, which is table salt. But you do have it there. So keeping in mind that sodium, Na, and potassium, K, are essential to your diet. You do need those to survive. Lithium, you probably have heard of as in batteries. We have lithium batteries. These are the batteries that tend to blow up in your hoverboards, your cell phones. But they are getting better depending on how you use it. You can have a battery that doesn't blow up. It's also used in medications, particularly to counter the side effects of bipolar disorder. So if you are diagnosed bipolar, your doctor might prescribe lithium tablets for you. And when you take lithium, it kind of stabilizes your emotions and mood and bipolar disorder. This is a lithium battery, just to look at how a battery works. Basically, a battery is going to have two electrodes in it. We have a positive electrode over here, and we have a negative electrode over here. In between, we have an electrolyte. This is a substance that wants to prevent the flow of electrons through it. And we have our lithium starting over here, and our lithium wants to move across. And as it's going to move, it's going to carry that charge with it. So it goes across to there. This electrolyte is going to make that really hard for that lithium to do, but it constantly wants to do that. If I attach a wire to this side and then attach it over here, so I skip that electrolyte, it makes it a lot easier for lithium to do so, and as lithium moves through, I give that charge out, and that is what I call electricity, that flow of that charge. So again, a battery is pretty straightforward. You have two electrodes. This electrode is positively charged and wants to give things, or give electrons pretty much, to your negatively charged electrode. We have something that is blocking that, so it's not allowed to do that. And then when I connect a wire that allows it to do it, it's going to take that wire path because it's easier to flow through there than it is through this electrolyte. So there's your crash course on how batteries work. Our second family, so moving on with our periodic table, our second family is the alkali earth metals. These are going to react by losing 2 electrons, which is also pretty easy to do. But again, it is also easier to lose 1 than it is 2. So these are slightly less reactive due to that fact. They are also only going to be found compound in nature because, again, it is still pretty easy. Ca is calcium. Calcium is, again, essential for your for living in your bone structure, things like that. And magnesium is an alloy for lightweight and strong metals. So a lot of times we do combine magnesium with iron and carbon to make different types of steels. But again, losing 2 electrons makes this fairly simple to react with. But these are your alkali earth metals. So anything in the second family there. Our next group is families 3 through 12. If you look at your periodic table, this is kind of that indented from above kind of section there. These are your transition metals. They are going to vary in their reactivity, but generally they are going to, the further left they are, like in group 3, are going to be more reactive than in group 12. These do have varying different properties and uses. For example, you have iron, which is essential for your blood. That's hemoglobin. Iron allows your blood to actually carry oxygen to your brain. This is what gets replaced if you have lead poisoning, actually. Lead will replace the iron in your blood, making so it can't move that oxygen, and therefore your brain won't get oxygen and you will slowly go kind of mental. You will get like memory issues and things like that because your brain's being deprived of oxygen. It's getting lead instead of the iron that carries the oxygen. Gold and silver, Au is gold, Ag is silver, are used in jewelry. Gold is extremely malleable and can be made into different shapes, and silver the same. Gold does not really tarnish, but silver does. So gold technically has a little more value to it in that aspect of jewelry, but jewelry in general is just for show. Copper we use in pipes and wiring. Again, you probably have heard of people going into houses and stripping their houses of wires because it is getting more expensive. Next we have metals in mixed groups. These are the elements in groups 13 through 15. Not all the elements in these groups are metals. That's why they are mixed groups. You get some metalloids and nonmetals in here as well. But the metals in here, for example, are aluminum. Aluminum, again, cans, airplane bodies, very big variety of different uses. Sn is tin. Tin is used to coat steel and iron so it doesn't rust. Zinc is also used for that purpose. Pb is lead, keeping in mind lead is poisonous. And it was used in paints back in the day and also in piping back in the day. Lead was used for a lot of different things. In fact, lead was very important that we named a planet after one of the Roman gods for lead, which is Saturn. Saturn is the Roman god of lead. And it's even the jewel of our solar system. I mean, like, that's like the coolest looking planet by a lot of people's purposes because of its rings, how important lead was back in the day for these different structures. Our next group is our lanthanides. These are found at the bottom of our table. They are the top row of the bottom portion. They are your rare earth metals, if you want to call them that instead of lanthanides. That's their other name. They are mostly used as trace amounts in alloys to improve other metals because, again, all these elements on here are easily combined with different other elements on there to make stronger and better properties. We call those alloys if one of them is a metal. Nd is neodymium. Neodymium is strong, and you notice the magnets that I have around those really strong magnets I use are those strong magnets found in hard drives of computers. Our last group of metals is right below our lanthanides. These are our actinides. The first 3, or I'm sorry, the first 4 are found naturally. The other ones are going to be made in labs. They are very heavy and they are very unstable. And they go through decay very fast. We make them in labs by just slamming protons together and seeing if they stick, because again, our elements are defined by the number of protons. So if I take a whole bunch of protons, just shoot them at each other in the hopes that they are going to stick together, and if I can replicate that twice, then I consider it a new element and I add it to our list. A lot of these, at least past the first 4 here, really don't have substantial uses because they decay too fast. They don't stick together very well. But your actinides, which is your actinium, thorium, palladium, and uranium, are used for different radioactive uses. For example, uranium you probably have heard about using for nuclear weapons or nuclear power plants, nuclear submarines. We'll get into that when we talk about radioactivity.